everyone to join our once-a-year summer school. We've been carrying out this summer school for many years. So this year, the first week is about removal lemmas and regularity lemmas. So it's probably not an understatement to say that regularity lemma and removal lemma is one of the most important advancements with graph theory in the past 8 years. And this first week, we have the pleasure to have an expert on this topic to tell us everything about removal lemma. So we have the pleasure to have Professor Lior Gishboliner from the University of Toronto. Pleasure here. Pleasure to have that podcast. And yeah, so let me begin. So I also prepared some lecture notes. I guess I'll send them to one, just like they'll be online later on. So let me start. So if you have any questions, please ask questions. So the general topic is lemmas, and we'll be talking about different aspects of this. But let me first start by saying what the removal lemma is. So the graph removal lemma. So this was proved. It implicitly follows from the work of Nurta and Temeradi. Okay. And it takes the following. So for every graph H, so we think of H as a fixed graph, and for every epsilon, there exists some delta, the function of the graph H and epsilon, such that if P has n vertices and at most delta times n to the P of H for P of H, then we can make G H3 by removing most epsilon n squared H. So very roughly speaking, what this is saying is that if the number of copies of H is small, then we can actually destroy all of these copies by deleting a small number of H. And the way we quantify this is that the number of copies, we look at this as a fraction of the total possible number of copies. So of course, we cannot have more than n to the P of H. And we say the number of copies is at most a delta fraction of the largest possible number. And then here, this is similar. So, of course, the graph has at most n choose 2 edges. So, trivially, we can delete most n choose 2 edges, something like n square edges. And we say that we can delete an epsilon fraction of all potential edges to make it H3. Okay, so let me just reduce the definition that I will use. So I will say that G is epsilon far from H3 if we have to delete the epsilon n square H. Make it H. So if I restate this theorem, if I take the contrapositive, what this theorem is saying, or equivalently, if G is epsilon far, from H3, then G has at least delta n to the G of H for P of H. So this statement is exactly equivalent. Okay, so this might look like a simple statement, but actually this is quite a difficult theorem. So now it's a standard theorem, but as you will see, the proof is quite sophisticated. So I want to explain how this is proved. I will not give all the details. So one remark I want to make, so if G is epsilon bar, then so if G has epsilon n squared H disjoint, copies of H, then it is epsilon bar. Right, so H disjoint means that these copies share no edges. Right, so why this is true? Because if we have that many copies and we want to have no copies, then we have to delete this one edge from every copy. So we have to delete edges. But actually, the reverse implication is also true after constant factors. What I want to say. So if G is epsilon bar, then it has epsilon over the number of edges of H. There is a constant factor here, n squared. Edge disjoint. So let me explain why this is true. So the proof of this, here, so the proof is we take a maximum collection, as large as possible, of edges joined copies, and delete all their edges. This makes G H3. Because if I take a maximum collection of H disjoint copies, then every other copy must intersect one of these, must share an edge with one of these, because else it's not a maximum collection. So if I delete all of their edges, then I have no copies of H then. And if I assume that G is epsilon bar, that means I have to delete at least that many edges, and that means that in my collection, I must have this many copies, else I delete. Okay, so this remark, the point is that these two definitions are equivalent. So being epsilon bar is the same as having essentially epsilon n squared after constant H disjoint copies. These two things are there questions so far? So now I want to start going towards the proof of this theorem. So we will need the notion of a regular pair. So let me define it. Epsilon regular pair. So we consider a bipartite graph. Bipartite graph. I'll write it like this: xy. That means that the parts are x, y. It's called epsilon regular. If for every x prime in x and y prime in y, such as x prime is the epsilon times x, and y prime is a split epsilon times y, it holds that point. So let me write it and then I'll explain. We have this inequality, and this notation D. So D of xy for the density so this is the number of edges between x and y divided by size of x times the size of y. So this is the total possible number of edges between x and y. And we ask what fraction of these are actually edges. And this is called the density. So what is this definition saying? Saying that xy is epsilon regular if whenever I take a big set in F, so x prime is kind of big, is a split epsilon concept, and another big set in y, so y prime, the density between x prime and y prime is essentially the same as the density between x and y. Okay, so these two densities differ by most of the time. So what is this definition about? So the way we want to think about it, this is saying that this graph is randomized in some sense. So if we chose the edges between x and y as random, for example, with probability 1/2, we expect this phenomena to hold. So if we chose them as random, then this density will be roughly 1/2 and this density is roughly 1/2. So they will be very close. Okay. So the idea of this definition is that this means that the graph is random in some sense. So it mimics random. And the important property that we'll use is called the counting lemma. I'll state the general form of it. For every gamma, there exists some epsilon, such as. So let V1 to VR be a disjoint set, vertex set. Vij is epsilon regular for every I. Okay. Then the number of R clicks V1 R for VIs and VI is following. Let me write it down. Okay. Let's try to understand what this expression is about. So here I just have the product of the sizes of it. Here I have the product of all them. Now let's ignore this plus minus gamma for a second. It's like an error term. Now imagine that, so the setting is that I have this set. Let's imagine, I don't know, let's say R is equal to 3. So we have V1, V2, V3. Imagine that I choose these edges at random. Okay, so imagine that I chose here the edges at random with probability V1, V3. So that's the density I want to get. So that's the density, that's the edge probability I'm using. And here I use V1, V2. And here the V2, V3. So imagine for a second that we do this at random. So how many triangles do we expect? So it's exactly V1 times V2 times V3 times the product of the density. This is exactly the expected number of times. And what this theorem is saying is that actually it's enough, you don't need to look at a random graph, it's enough to assume that it's epsilon regular, and you can still get this correct triangle count, like in a random graph, but we have some error, which is this gamma. Okay, so the way this works is that we choose what error we want to have. And then there is some epsilon. This lemma gives us some epsilon, such that if we have epsilon regularity, then we can have at most this error. Questions? Okay. So let me prove this. Let me show you how the proof of this works. I don't want to do the general proof for general R. I'll just do the proof for R equals 3. The general proof is very similar. It goes by down. So let's take the case that R equals 3. So in this statement, here I can assume that the densities, this Bi, Bj, are much bigger than epsilon. That it's much smaller than the density. Because, well, I can choose epsilon. I can assume that this guy, right? And therefore, that I can choose epsilon. Epsilon. The reason I can assume it at least gamma is that otherwise this statement becomes tricky. So you can think about it. So in particular, if you take minus gamma, then it's less than 0. So that direction is trivial, and you can also think like upper bound. So I will always assume that the densities are much bigger than time. So the statement that I want to prove is that if so let's be positive if V1, V2, V3 satisfy that they all have densities D, and they're all epsilon regular, where what is epsilon? So it turns out that for this case, it's enough to take epsilon b over 2. So we can take it as small as we want, just b over 2. Then there are the number of triangles. You see, for the following form, so B1, B3 times D cube. So D cube is how much I expect, right? Before the density 13. And then I have some error, and the error in this case will be most for now. So just to show you a proof of error. So let me prove you this statement.
Yeah.
So what we'll do as follows. So for I equals 1 and 2, let BI be the set of all vertices in B3 such that okay, so what is BI? So we have B1, B2, B3. So BI is all vertices in B3 here that have a small neighborhood to BI. So say B1. Right? So B1 are all those vertices that have small neighborhood to B1. And what is small? Small means, well, we expect at least D times B1. And so let's say it's less than D minus S. So first thing I want to show you is that this set BI is actually small. So there are only very few vertices that don't behave how we want. So again, BI is less than epsilon B3. Okay, why is that true? So otherwise, so observe that the number of edges between BI and BI. So how many edges do I have between BI and BI? So I can bound it the following way. So it's small BI, and each of them has a small B minus epsilon. Yeah. So this means that the density between these two sets is less than B minus. Right? Because remember, the density just means taking the number of edges and dividing by the size. Okay, but I claim that this is impossible because of the epsilon regularity. Right? So if the I is at least epsilon B3, then this contradicts the epsilon regularity of BI
and V3. Right, so we have V3, we have VI, and here we have this set V3, VI, sorry. So, and we know that the density, so the density between the V set, between VI and V3, is at least V, but the density between VI and the smaller set, VI, is less than V minus epsilon. And this contradicts the definition of epsilon regularity, right? And the definition is difference must be at most. So this is only possible if this set is very small. Okay. So this proves this thing, and now what we can do is to now fix any V in V3, which is not in V1 and not in V2. So the number of choices for V is at least 1 minus 2 epsilon times V3 by this way. So now we have this V that we take, and now we look at its neighborhood in V1 and in V2. And those two sets are big. So they must have many edges by the regularity, and this way we will get many points. So let me write it down. So we have the neighborhood in VI of V at least epsilon times VI for I 1 and 2. And therefore, by the epsilon regularity of V1, V2, the number of edges between the neighborhood in V1 of V and the neighborhood in V2 of V is at least V minus times the product of these neighborhoods. And each of these is large. This is V minus epsilon, V1. This is minus epsilon times V2. So this whole thing is at least V minus epsilon cube times V1 times. So what we saw so far is that if we take any V, which is not in any of these Z sets, then V is contained in many triangles. So this number of triangles. So now we will just sum over. So we can multiply this by the number of choices for V, and that's how many triangles. Okay. Yes.
The number of neighbors of V and VI is epsilon times VI, but epsilon, I thought it's going to be an schema.
You're right. I see the thing. You're completely right. Absolutely correct. You're right. So what we actually know is that it's at least V minus epsilon times VI. Now, what I actually want is that this is at least epsilon, because then I can use the regularity. So I can say that it's at least epsilon if epsilon is small enough. So here I use the epsilon is zero. But you're exactly right. Here's where we use the epsilon small. Okay.
Maybe the condition is epsilon equals to 0 to another polynomial, because the inequality was not that the right hand side is
You are
maybe we need epsilon to be sufficiently small.
Yes, you're right. I mean, the statement is still true, even if it's less than zero. But you're right. To make this useful, we want to assume epsilon. Okay. One question? Okay. So let me finish this proof. So this means that the number of triangles is at least. So I'm going to take this estimate we got here for a single v and multiply it by the number of v's. So I'm going to get 1 minus 2 epsilon v minus epsilon cubed v1, v2, v3, and okay, so this is at least v cubed minus 5 epsilon, maybe not 4 but 5 times v1. So this is the proof of the concept. Okay. So let's continue. Let's report. Yes. It does depend on the R. No? But it is. He gives that R if you must and R will. That's really the only example of R. I assume it has to depend on R. I don't have to open my head and just other than in the proof it does depend. By month. Okay. So now we have the counting length. Now the question is, can we even get this kind of thing, epsilon regular hypertext graphs? And there is a very, very important result by Semeredi, which is called the Semeredi regularity lemma, which says that any graph we can decompose into hypertext graphs, such as most of them are epsilon regular. So let me say this result. Three epsilon. For every integer t0, there exists some other integer t. Such that every graph G has an equipartition vertices into T set V1 up to Vc, where T is at least this T0 that we gave as a parameter, and it knows this capital T, such that all pairs ij between 1 and t, except most epsilon t squared, are epsilon regular. So let me explain the statement. So first, let me tell you what an equipartition is. So this just means that the parts have the same size, or maybe they cannot have exactly the same size because of the reducibility, but they differ by most one. Okay, so this means that vi minus vj is most one for every. Now, when we use this theorem, I don't want to bother with the divisibility issues. It's just a technical issue. It doesn't really change anything. So I'll just assume always that they have the same. Okay, so what is the statement saying? Saying that any graph, for every graph, we can find the partition of the vertices into T set, V1 up to Vt, where T, well, we can make T large enough by choosing this parameter T0, that's the point of it. But the main thing is that this T is not larger than the capital T, and the capital T depends only on epsilon. And the main property that we get is that almost all of the pairs Vi, Vj are epsilon-based. Questions about statement? So I will not prove this because I want to give you a sketch of how this is proved, and I'll skip some of the key details. Well, okay, so here's a sketch. So the key definition that the proof uses following. So for a partition, T, V1 up to T, fine. So following function, we take a sum over all indices I and j, and then we take Vi, Vj over n squared. So this is kind of the weight of the pair, and we multiply this by the density of Vi, Vj squared. This is an important function. This is called the mean square density. It's the mean or the average of the square of the density, sometimes called energy. Okay, and so this function has two important properties. So this is a lemma that I will not prove. So first of all, if Q defines P, then the energy of Q is at least the energy of P. So if I have some partition T, this is T, and then I take a refinement, which means I take each of this part and I break it down, and this is now Q, then the energy does not decrease, it can only increase. So this is the first important property. And the second important property is that if an empty partition it has a T, epsilon T squared, epsilon irregular pairs, then T has a refinement Q with such that the energy of Q is C, the energy of P plus epsilon. So the second important property is that if P is an equipartition and P does not satisfy the conclusion of the theorem, so if we have too many irregular pairs, then we can actually get a refinement of P, Q, where the energy not only that it doesn't decrease, but actually it increases by some substantial amount. By science. Okay. So again, I want to give you a sketch of how this is proved. If you want to see the full proof, you can find it online. I have lecture notes to the proof for find other lecture notes. So let me explain you how, again, let me give a sketch, but explain how this proof. So we start with P. This is P. And suppose we have a pair, the IBJ. Suppose the IBJ is not regular, is epsilon irregular. So what can we do with this? Well, this means that we can find some set here, let's call it Vij, and we can find another set here, let's call it Vji, such that the density of Vij and Pji is very different than the density of Vi and Pj. So just by the definition of a epsilon regular pair, if a pair is not regular, then we can find big sets here and here, such that their density is very different than the density of Vij. So it differs by a big size. And we have also the Vij big epsilon Vi and Vji with this epsilon Vj. Okay. So now suppose that we do this for every pair that is not regular. Right, so now I did it for Vi and Vj, but maybe also Vi and Vk is not regular. So I can find here a different set, Vik, which is not regular, and here a set Vki, and those are witnesses to the fact that this is also. So what the proof does is actually do this for every pair, which is not regular. And then here I have many sets, and I don't know how the sets interact. So what I have to do is take the Venn diagram. Okay, so then what we do is take Venn diagram of Vij over all j. And this is the partition Q. So this is. So how many parts do I get? So here one important thing that I forgot to write here is that Q is not large. So actually Q, the number of parts in Q is at most P times 2 to the P. So why is it at most that? Because in each part of P, I have this P set, and I take the Venn diagram, so that's at most 2 to the P. Other questions for this so far? Yes. Okay. So Venn diagram means, if you have, so this is Vi, and we have some sets. These are those sets Dij. Maybe those are the sets. And now the partition is, this is one part, this is another part, this is another part. Just all the parts in the Venn diagram are the partition. More questions?
Okay.
Yes.
If I, how do I make that requirement also, yeah, active?
So what I showed does not say that Q is an active partition. So the way the proof works is that we do this step, and at this step, Q is not an active partition, right? And then there is an additional step of making Q an active partition. And I want to skip this because it's very technical and that's not the most important idea. So, but since you asked, so the way this works, so you get Q. So let's say this is Q. And the way you make it an equipartition, you choose what the size of the part is going to be. Then you just chop up these parts into this size. So you divide them into equal size parts. Also here and you can show that. So an extra step, so I'll just write it. Then I leave it. So there exists an equipartition Q prime with the energy of Q prime is a T, the energy of Q minus delta, and the size of Q prime is at most some function of delta and the size of Q. So we choose this delta. So what is this delta? We want to choose delta to be epsilon to the fifth over Q, right? Because at this step, we are gaining epsilon to the fifth, and we don't want to lose this gain. So we are willing to lose a little bit. We're willing to lose something small. So the fact that I'm not going to talk about, other than this, is that you can get actually an equipartition by chopping up this part this way, where the energy only decreases a little bit, and the number of parts is still values. More questions? Okay. So I claim that with these two facts, or actually with this fact number 2, we can prove the regularity. So let's recall what the regularity lemma is. So we want an equipartition where the number of irregular pairs is at most epsilon squared. And what this is telling us is that as long as this is not true, we can find a new partition where the density is significantly bigger. Now, what we want to use now, an easy fact is that for every partition P, the energy of P, well, if it is 0, this is really easy, but also it's most 1. Right? Because this number is at most 1. And here we have weight that sum to 1. Or to 1. Okay, so now, before I continue, let me just say that a partition like this, with these properties, called epsilon regular partition. Now we can prove the regularity lemma. So start with an equipartition T0 into T0 parts. So for I is 1, or say I is 0, if Pi is not epsilon regular, then the derivative Pi plus 1 such that the energy of Pi plus 1 is the energy of Pi plus the epsilon to the 5 over 2, and the size of Pi plus 1 is most, let's say, Pi times 2 to the Pi. Actually, I'm cheating here a bit because there is also this extra step. So this is the bound we get from here, right? But then there's extra steps where we make it into an equipartition. But let me not worry about it. So there will be some, maybe an extra function of Silot. And to make it even nicer, let me just write 4 to the, yeah. Okay. Now, the key point is that this process cannot continue forever, right? So this process ends in its most 2 over epsilon to the 5. Okay. Why is that true? Well, at each step, the energy increases by at least this number, but it cannot increase beyond 1, so the number of steps most 1 over. Okay, and this is the proof, right? So at some point, this process stops, and it gives us the epsilon regular equipartition, like in the statement of the regularity lemma. And the key point is that the number of steps depends only on epsilon, and so the final size of the partition only depends on epsilon. Questions? Okay. So the next thing you can ask yourself is what is this number t? How does it depend on epsilon t? So what do we get from this proof? Well, 4, 4, 4, so on to the zero, where the number of exponents here is at most is 2 over epsilon 1. Right? Because each time as we iterate, we gain 1 exponent. So we go from a partition of size ti to a partition of size, let's say, 4 to the ti. And so each time, each step in the process, we gain an extra exponent. This is power type. Power type. The power function. Okay, so this is usually defined as 2 yes, 2, so on k times. The base doesn't really matter or 4. Okay. So this proof gives the power type behavior, and turns out that actually this is not avoidable. So there's a theorem like ours, 1997, that there exists a graph that means power of 1 over epsilon to c parts in any epsilon regular. So for some time people didn't know if this proof is optimal, so it gives huge. So this is a very fast growing function. Like even if you take an epsilon of the 0.1, this is a huge number. So for some time people didn't know if this behavior is necessary until Gowers proved that actually you must have this tower type behavior. So there exists graphs where if you want to get an epsilon regular partition, the number of parts you need to take is at least the tower. Now the height instead of 1 over epsilon to the 5th is some other power of epsilon. So I think Gowers proved it with 1 over 16. Now I think by now there are better bounds. The bottom line is that we need this tower type to defend representation. Questions? Yes. Well, yeah. So in this, so here I imagine that T0 is 1, right? So here I don't make any lower bound requirements. Question is, does Gowers' proof work also to give something like this? And I'm not sure. So if we insist that the partition size is T0, can we actually put also here T0? Okay. Yeah, so here, let's imagine that T0 is 1. Don't make lower bound. Also, another thing is that usually this T0, like usually, so we will see in a moment why we need this T0, why it's useful to have this graph. And usually in these proofs, you take T0 something like 1 over S. Like you choose T0 depending on epsilon for some reason in this. So this really doesn't make a big difference. So really what makes the function big is the height. Our questions? Okay. So now we go back to the removal lemma. So now we have everything we need to prove it. So let's do that. I'll only prove it in the case that H is a triangle. I think that's the only case that's proved in the Bristol paper, and also have all the main ideas. So this will make it a bit easier for them. Of the triangle removal lemma. Okay, so we are given a graph which is epsilon far from triangle 3. And what we want to show is that G has a delta is delta n cube prime. And so the way this proof is going to go is that we'll first take a regular partition, apply the regularity lemma, and then we will delete some edges. This is called cleaning the graph. So let me show you how this works. So let V1 up to Vt be a regular partition, an epsilon regular, let's say a gamma regular partition. Of size at least P0, which is, so I take P0 to be 10 over epsilon, and also gamma I take to be C, so epsilon over 10. Okay, so I apply this lemma, but I apply it with the parameter gamma and with parameter T0, and I choose this gamma to be epsilon over 10. So I need some constant here, and also the T0 is 10 over 10. Okay, so now I have this partition, and now I'm going to clean the graph. So I'm going to delete edges at the following size. So delete the following edges. So first, going to be edges inside the part. Second, edges between Vi and Vj with such that the density of Vi and Vj is less than epsilon, less than, let's say, 2 gamma. And 3, edges between Vi and Vj such that Vi and Vj is gamma irregular. Okay, so why am I doing this? So before we had the counting lemma that told us that if we have 3 sets where all of these are gamma regular, if all pairs are gamma regular and density is 2 gamma, then we have many triangles. Right? And now, so I can only do something like this if these pairs are gamma regular and efficient depth. So I want to get rid of all the edges which are not like that, which I don't have control over. So first of all, I have no control over the edges inside the class. Right? So I'll just delete all the edges. Also, if a pair Vij has 2 small densities, then I'll delete all the edges there. And also, if a pair is gamma irregular, I'll delete. Now, as one of you pointed out, in the second of the counting lemma that I wrote, I actually need to take this regularity much smaller, and because otherwise there was this expression there that was less than 0. Let me avoid this. So just don't want to do it now on the board. Probably mess something up, but you can imagine that you can take this gamma prime much smaller than this gamma, and then this will be something. So now the plan is to count how many edges I delete. So I want to say that I deleted only few edges. So let's consider each of these three types and count how many edges we delete. So type 1. So we deleted the smallest sum. We deleted small t times n divided by t equals 2. Right? Because I have two parts. They're all of the same size. So each of them has a small n over p edges. And I could not delete more. So this is a small p times n over p squared, which is n squared over t. So now what I'm going to use, so this is a small n squared over t0, because t is 0, and what I'm going to use is that t0, right? So because of the choice of t0, this is a small epsilon over 10. So the reason we want to have t0 in the regularity lemma is we want to say that the number of edges inside the part is small. We don't have any control over them, so we want it to be small. Okay, so this is edges of type 1. Okay. Now let's do edges of type 2. So we deleted the small sum over all I n, and we only delete edges if the density is less than 2 gamma. So we can write 2 gamma times pi times k. So let me take this gamma outside. So this is gamma times this sum. Can someone tell me how I can upper bound sum here? Yes, right. So that's so n squared 4. So this is the small 2 gamma times n. Very good. And this is so I chose gamma to be small, right? So this is the small epsilon over 5. Yes. So here we use the pairs which are sparse, don't contribute any. So 3. In 3, we delete edges between pairs which are not regular. And now we want to use this. We have two of these pairs. So we delete the small. So we have a small gamma times t squared. That's there. And between vi and vj, we can delete the small n over t. So this is gamma. But also, which is the smallest epsilon over n. So in total, we see that we deleted two edges. Right, so in total, we deleted less than epsilon n. Now, we started with the assumption that the graph is epsilon far from being signed. That means that we cannot make a triangle free by deleting so few edges. So after we clean the graph, there must still be a triangle. Okay, let's do that. clean graph, but there is let's say between VI, VJ, and VK. So we can go back for a second. So, right, so the statement of this small issue we have with the statement of the counting lemma, let's just make that okay, right? So actually the bound that we have was something like this. B1, B2, B3. Just going back to the remark of one of the references. So this is actually the boundary dot, and here there's no problem if you don't see over time. Right, so this is still a positive number. So you're right that when I lower bound is like Q minus 5 epsilon, then this is not a good case, but let's ignore the lower bound. Right. This is the bound. Okay, so now going back to the proof of the removal lemma. So we clean the graph. After we clean the graph, there has to be still a triangle somewhere. Now it cannot have two vertices in the same set because we deleted all the edges inside. And also, so it has to go between some VI, VJ, and VK, and also all of these three pairs must be gamma regular and must be dead. And otherwise we delete. Right, so VI, VJ, VK, VI, VJ, VI, VK, and VJ, VK are gamma regular and have density 8 to gamma. And therefore, by the counting lemma, there exists some polynomial in gamma times VI times VJ times K, a triangle. And now the final step will be to say that each of these quantities, so the sizes of the set, VI, VJ, VK, is at least n over t. So I get n over t. Right, so the sizes of the set are n over little t, number of parts, but we know that the number of parts t is the most capital T. The capital T we get from the third lemma. So we get this. We get this load bound. So now we're done, because remember, what we wanted is that we have delta and cube triangles, and here where delta depends on the epsilon, and here we have an expression of this form. So we can set delta to be some polygamma divided by polygamma is some explicit expression. I just don't want to questions. we proved the removal lemma. So again, we can ask about the dependence between the parameters. So this proof gives that 1 over delta. Remember that in the removal lemma, we have this parameter, we have epsilon, and then we have delta of H and epsilon, which we denote by delta. Right, so what this proof is that 1 over delta is at most some tower of height polynomial in 1 over epsilon. Right, so this, again, this tower function is 2 to the polynomial in 1 over epsilon. So why do we get this bound? It's because we have this, what really determines the behavior is this EQ. Right, and C comes from the regularity lemma, and we know that C can depend at the tower time on the side. Now there is a major problem to improve this. So the only improvements we know so far is by Fox in 2011, and he proved that 1 over delta is at most tower of height, which is only logarithmic in 1 over delta. So it's still a tower, still a huge function, but the height of the tower, instead of being polynomial in 1 over epsilon, it's only logarithmic. And this is the base bound, So there are a few proofs for this. So Fox has a proof for this, and afterwards there are 1 or 2 other proofs, but we don't know. This is an important problem. I'll not talk more about it, just so you know. Now the problem we'll talk about, so we'll start talking about now, and it will be the topic of tomorrow. It will be the following question. So when is delta H of epsilon polynomial in epsilon? Right, so how polynomial in epsilon is the best we can hope for. So for which H can we actually get it? Now, it turns out that even though we cannot improve this upper bound in general, we can answer this question. So we know that for which H it is polynomial. So the theorem that we'll prove tomorrow by Alon from 2002 is that delta H of epsilon is polynomial if and only if the graph H is bipartite. Okay, so there is one direction of this theorem that's actually pretty easy. Another direction which is harder. So let me tell you the easy direction. You want to guess what the easy direction is? Yes. Sure. So for that direction, let me remind you of an important theorem in extremal graph theory, the Kovalishov-Grant theorem. And I will need what's called the supersaturation form of this. As following, so if G has epsilon n square edges, then G has polyepsilon n to the power s plus t copies of K. Okay, so you might have seen the Kovalishov-Grant theorem saying that if G has sufficiently many edges, then it has one copy of K. In fact, the same proof gives you that if you have epsilon n square edges, then you have this number. Okay. So now this implies that if H is bipartite, then this delta is polynomial. Let me explain to you why. So if H is bipartite, so suppose if epsilon far from H3, then in particular, the number of edges is epsilon n squared. Right, so this is a trivial implication because if we had less than these edges, we just delete all of them, and there will be no compensate. And so by the theorem, by the Kovalishov-Grant theorem, the number of copies of H, so if H has S vertices in one part and T vertices in the other, and the number of copies of H is equal to the number of copies of AST, which is G polyepsilon times n to the number of vertices. Right, so it's just applied just because H contains. So this is delta polynomial. Okay, so this direction is easy, and tomorrow we'll prove the other direction, and if you'll see it's kind of an interesting proof. So it uses something from additive numbers. So it's related to we will use a construction of sets which don't have three-term arithmetic progressions. So you'll see this connection. Any questions? Yeah.
What is the best known lower bound?
Yes, very good. So the lower bound we will show a lower bound that is bigger than any polynomial, right? That's what I promised you here. So the lower bound we will show is that 1 over delta is at least 1 over epsilon to the power of log of 1 over epsilon. So this is not polynomial, right? It's bigger than any polynomial in 1 over epsilon because this thing is growing, so it's bigger than any number. But so it will prove the theorem, but it's still very, very far from. Okay. And this is the best lower bound. Yeah.
But you're asking what do people, for example, what do you believe is correct?
I rather don't know. Probably I would guess. Okay, from what I know, I think people believe it's not. That's not tower.
Oh, so people do not believe in the power.
I think so.
But the regularity is not power. So
It is. So then you need some other. So one thing we'll talk about tomorrow is that this triangle removal lemma is related to what is called Ross theorem. And so we'll see this tomorrow. It's a statement about sets which have no three-term arithmetic progression. And you can use the removal lemma to prove this. You get kind of the tower type found, but this was improved, like dramatically. So we know much better bounds. So I'll mention somehow for this.